All right, so we'll go ahead and get started. And today we begin on page 38. So open to page 38. So there are some announcements and there's the calendar, but I want to make sure everybody's finished with the quiz before we make those announcements. So let's just jump in to our new technique for today, integration by parts. And I'll also say that I know that this presentation will be shortened because we had kind of a long quiz that we're finishing up. It's a fairly straightforward technique. It's very procedural, so I think it'll be okay. We won't have a chance to do everything in the notes during class together today, but that's all right. I think it's a pretty straightforward technique once you've seen it a couple of times. So number one, are we able to calculate the simple looking 3x cosine of x? Two very simple functions, 3x cosine of x multiplied together. Can we integrate this thing? Can we find an antiderivative? And the answer is no. I mean, the only technique we have is, number one, is it one of the 8 things on our reference sheet? Number two, can we do a u substitution and make it one of the 8 things on the reference sheet? And there's nothing we can do here. 3x and cosine of x are the two functions, and they have nothing to do with each other. So there's no u substitution where the derivative of one part is going to equal the other part. So new technique, it's called integration by parts. And there's a formula which looks like a whole bunch of gobbledygook. U dv is equal to uv minus integral of v du. You're going to throw that on the formula sheet. But let's just see if we can work through that formula. I'm not going to derive it here because we're a little bit short on time today, but I'm pretty sure there's a derivation in the book. If you're dying to see one, stick around for 2 minutes after class and we can look at it together. But let's just see if we can use it. So we're going to do a few integrals together with this new formula. And the first one we'll do is 3x cosine of x dx. So what I do every time I do one of these integration by parts things, and we'll give you some hints today about when this technique has potential, but every time I set it up exactly the same, it always looks like this. Top row is u and dv, bottom row is kind of the opposite. So it always gets set up like that, always looks the same. So here's what you're going to do. You're going to take the 3x cosine of x dx and you're going to split it up into 2 different pieces. Part of it you're going to stick in here in the u, and the other part you're going to stick in the dv. And don't write this down just yet, but for example, one thing we might do is put cosine of x here and 3x dx over here. Don't write that part. But everybody agrees that that integrand has been entirely split up, right? Everything that we had to start is there somewhere. So that's one choice. What's another choice? The other way around. All right, and I'll give you a sense as to like why we're going to make which choice. But for right now, I'll just say this choice is not a good choice. We're going to put it the other way. 3x here, and then everything else has to be in the other one. So go ahead and write that part down. Turns out that's a good choice. And now once we've made this choice, which we don't know why we made it, let's go ahead and fill in the bottom row. This is where we have to start calculating. What do you think you need to do to the u function to find du? Take a derivative, right? The d says take a derivative. So the derivative here is, I'll put it in a different color, derivative here is 3. And then we're going to put the dx there. It looks the same as when we did u substitutions, where you'd always have du equals something something dx. Mm-hmm. That's right. The derivative of u just becomes 1, and then you stick on the du. All right, the other column, we have dv. What do you think we do to that thing to find v? Let's take an integral. So one side we're doing a derivative, one side we're doing an integral, an antiderivative. Integral of cosine of x dx, sine x. You could put the plus c there. We never put the stamp in the middle of this technique. We'll stamp it once at the end. It's not wrong to put it, but it's going to cause more work. We'll just put it once at the end. Okay, so we're just doing procedural stuff, no sense as to why or where it's going, but let's use this formula that we've got right up here at the top. Integral of u dv. Where do you see u and dv in my list of 4 things here? It's the top row, right? So that's why I set it up, because you put the entire integral in the top row, and then you have a formula here that tells you what that entire integral is equal to, all right? And then we'll follow the pieces. So let's use our formula. This guy equals, according to this formula, u times v minus the integral of v times du. U times v. U is over there, it's 3x, times sine of x, the v. Everybody see where those two parts came from? It's u times v. And then what's next in our mysterious formula? What is it? It's the minus, and then an integral. And then it says v times du. Todd? Sine x times 3 dx. That's it. So once you've written it, take a moment, make sure you believe that we got everything from that formula, looking at our 4 pieces over there in green and blue. Everybody see how the pieces come together in this black equation? Questions so far? Okay, so we've got this, and I'll say this, all we've done is traded the one integral for another one, right? We still have an integral in front of us. So this technique is only useful if we can actually do the integral in front of us. Can we integrate sine of x times 3 dx? We can. That 3 can pop right outside, and then sine of x is one of the 8 things we can do. So we ended up with an integral that was better, one that we could handle. So I think we're ready for our final answer. Again, the 3 can go where? Outside the integral. What's the integral of positive sine x? It's negative cosine. So I'll put in parentheses, negative cosine. And I said we were going to stamp it once. We do it right there at the end. So that's it. Just change those negatives to a plus in this case, and we're done. Any questions on any of the pieces? If we wanted to check to see if that actually works, there's no reason to believe that it did. What would we have to do? We would take its derivative, right? You can check any antiderivative. Finding antiderivatives is hard. Checking is easy. You take the derivative of your answer, and what are we hoping we get? 3x cosine of x. What derivative rule would we have to use to take the derivative of our answer? Is the multiplication of product rule, right? Okay, integration by parts. This formula is our way of undoing the product rule. Think about how hard the product rule might be to recognize if somebody's done it. If you just had to look at the derivative of something that came from a product rule, right? If you actually use the product rule on this, first times derivative of the second plus second times the derivative of the first, we'd have to be incredibly lucky to recognize that coming from a product rule, right? This formula right here sort of takes out the luck and makes it procedural. It's our way of undoing the product rule. So because we're a little short on time, we're not going to check. But I'd encourage you later on to take the derivative of that thing. For some reason, there's this extra 3 cosine of x. And some nice stuff is going to happen. You'll end up getting the 3x cosine of x that we want. Questions on the process? Okay, one observation here. The first thing I wrote down in green was the other choice. I had cosine of x here and 3x dx over there. And I said that was a bad choice. So let's talk about why that's a bad choice. How do you know which one you should put into which slot? Okay, when you take what do you do to cosine in this case to go down this column? You take its derivative. Okay, so derivative of cosine, negative sine. Fine. What do we do to 3x? Antiderivative. It becomes x squared and then some number in the front, right? Okay, when it comes time to do the integral, this guy here would basically be an x squared. That x squared is the v, yes? So when it comes time to do the integral, we'd end up with x squared times, that guy over there was sine of x, maybe it was negative. Is that, what is it? Yeah. Is that better or worse than the original integral? It's worse. We started with basically x cosine of x. We end up with x squared times the trig function. It's worse, right? So now hopefully we start to develop some intuition. How do you decide where to put something? Well, when you take an antiderivative, you really don't want it to get any worse. And that's one of the nice things about cosine. When you take its antiderivative, does it get worse? It pretty much stays the same. It turns to sine. But if it's an x over there, it gets worse. So you really want to pick something so that when you take an antiderivative, it doesn't get too much worse. And for the other piece, its derivative hopefully gets better, right? That 3x became just 3. That's why the last integral was doable. Todd? Yeah, if you have a sine or cosine, it is screaming to be placed over there in the dv because it doesn't get any worse when you take antiderivative. Good. E to the x is another ideal candidate for being over there, right? Because when you take antiderivative of e to the x, it stays exactly as it is. Good. Last thing for me, this formula, I can never remember it in terms of symbols, so I have a little pattern in my head. UV, when I write my 4 pieces out like this, which I always do, UV is that diagonal. VDU is this guy. I'll put a little minus sign in front of an integral. That's what I remember about integration by parts. We go on the first diagonal, minus the integral, and then go across to the left. Okay? All right, so let's try the next one on the next page. Okay, and oh, right, so there's that calculator thing. A few people had a chance to do this, so check it out later if you're interested. So there's part B on the next page. Before we do, we'll take our look at the calendar. Today we just finished our quiz. We're looking at integration by parts. This coming Monday, what's happening? It's President's Day. There are no day classes on Monday. No day classes on Monday. Anybody have a Monday night class? Monday night classes are on as scheduled. Okay, so we don't see each other again until Wednesday. Wednesday we'll talk about using tables of integrals. Wednesday is the last day of new material before our test. Friday, a week from today, a couple of things happen. First, the project on area is due 1 week from today. Second, we have our full period review day for test number 1, which is happening on Monday, February 25th. A couple of days after that is when I'm going to ask you to give me your grading choice. Do you want homework to count? Do you want questions of the day to count, etc.? Questions on the calendar? Okay, a couple of announcements unrelated to this class. Number 1, last semester I talked quite a bit about this free tutoring service online that GCC has subscribed to on behalf of its students. It was called Smart Thinking, and I gave some little sample information about it last semester. We're not going to go into near that much detail, but it is available to you again. There's the webpage. You just type in Google smarthinking.com. There's only 1 T in there. Your email address is your GCC one. Your temporary password is GCC. So I'd encourage you to just make a quick note of that webpage and your username and PIN or password. It's free. You can explore it. If you have no idea what it is, just ask me right after class and we can talk about it. Okay, next. There is some money available to GCC students, and I'm hoping you guys get it. First one is an International Travel Award where you can learn a foreign language by studying abroad. There's an application process. If you have any interest in this, see me right after class. Or email me and I can send you this document with all of the information. All right, this is a summer travel abroad program. Next, there are some scholarships available to women in public higher education. Lots of details. We're not going through them right now, but I have highlighted the important things. That's the dollar amounts, $750. Down here is $1,000. If you are a woman in public higher education, which some of you are, see me right after class or email me and I will send you this document. Last thing, this is the most important thing for most of you. If you go to the GCC webpage, down here on the bottom right, there are scholarships available through the GCC Foundation. This is an annual thing, happens every spring here at GCC, and it is something that I encourage all of you to think about applying for. There are a list of scholarships available by department. For example, there are some scholarships specifically given to engineering students. We're not going to look at that. There's also a list of the GCC Foundation scholarships. We'll come down here. The 25th anniversary scholarship, which is made on the basis of scholarship, financial need, and character. There is one of those valued at $800. The Hap Adams Award is based on that stuff there: loyalty, concern, discipline, love, and humility. For $275, there are 2 alumni scholarships for $550 each, minimum GPA, and you need to be planning on transferring. There is a long list of these scholarships here. I guarantee that all of you are eligible for many of these scholarships. I also guarantee this is the best odds you will ever find in terms of applying for free money. These scholarships are available only to GCC students. There are roughly 2,500 of you. I don't have a guess. Well, I have a guess. I have no idea how many students apply to these foundation scholarships every semester. I'd be surprised if it was as much as 10%. So maybe we're competing with 250 people for a whole ton of money. And again, all of you are eligible for many of these awards. The application process is fairly painless. There is a basic information thing you fill in right there. All scholarships require a personal statement. It's not very long. Some of the scholarships require a little bit more, but you can apply to a bunch of scholarships with one very short, very painless application. And I'd encourage you to think about it. Testimonial. Questions on this? Okay, I'd encourage you very strongly to look into this. There are good possibilities for money coming through. All right, let's take a look at part B. Integral from 1 to e of ln of x dx. ln of x, we can integrate that, can't we? What's the antiderivative of ln of x? 1 over x, right? That's the derivative. What's the antiderivative of ln of x? We don't know. It's kind of surprising. A simple function like ln of x, we have no idea what function has its derivative of ln of x. All right, guess which technique is going to work here? Integration by parts. Good guess. So we'll set our pieces up in exactly the same way every time, u and dv across the top row. Well, yeah, it's a great question. So we're in the process, we're in the beginning stages of learning a whole slew of integration techniques. Part of what we need to be successful is to just know the techniques, but another part, and this is the part you're asking about, is how do we know when to apply the techniques? We're going to try to give details at each step of the way as to when it's a candidate. At the moment, I'll just tell you that ln is a good thing to think about integration by parts for. So are the inverse trig functions, like if you had to integrate inverse sine of x. Integration by parts is an appropriate technique for that. But we'll try to give you hints along the way. Right now, there's a lot of techniques we don't have yet, so it's just like, well, we don't have much to try, so let's try this. Okay, across the bottom row. You bet it works? Wow, look at that, the eternal optimist. Okay, this one's kind of weird because usually there's 2 functions multiplied together and we split them up. But here there's only one function, ln of x. Okay, well, your choices are either to put the ln of x here or to put the ln of x there, right? If you put the ln of x here, what do you need to do to go down? Integrate it. Do we know how to do that? No, let's not put the ln of x there. So we put the ln of x over there, which means what is left over for the dv is just 1 and also the dx. Everything has to be there somewhere. Okay, so now we'll go down to the bottom row. In the first column, what do we take? Derivative. 1 over x, don't forget the dx. Yes, we will. Yeah, permanently. I mean, you're about to add to your list of things you know how to integrate. All right, to go down the second column, what do we take? Integral. Antiderivative of 1 dx is x. No need to stamp it with the plus c. We'll do that once at the end. Although actually this one, we're not going to stamp it all because It's from 1 to e. It's a definite integral, so there's no stamp at any point here. Okay, do you guys remember the arrows? Maybe draw the arrows if you remember them. So the first one is a diagonal. And the second one goes back to the left, minus an integral. All right, so let's put it here. The original integral equals, so just following our arrows, u times v, ln of x times x. All right, I'm going to put the x in the front just so it doesn't look like it's in the ln. Minus integral, that's part of the formula. And we go across the bottom row. X times 1 over x dx. Did we get an integral that we can do? We did, because miraculously x and 1 over x cancel and we just have to integrate 1, which is easy. So as you go through this process, like this is really the most important time for me, is when I write that integral, because not until then do I see whether or not this has any chance of working. I want to know if I can integrate the thing. If I can't, I haven't made any progress. So let's put, what do we need to put? So we're also going to put the 1 and the e back where they were. So it's still the integral from 1 to e. And what do you think we're going to do with the x and the ln of x? It's also from 1 to e. So I'll put the vertical line there. We're going to do 1 to e at the end, but just notationally, it still needs to be evaluated. Angus? Okay, yeah. So there's a little hint up here at the top. Just says if you have a definite integral, you write it basically just the way that we did. Okay, so let's keep going here. This thing equals x ln of x minus, what's the integral of 1 dx? X. And then this thing gets evaluated between 1 and e. Any questions on that? Okay, so I'm not so interested in plugging the numbers in. That's pretty straightforward. But I did want to include this just to be clear that the first part that pops out still needs to be evaluated between the numbers, right? It's not just the second integral that you get. Okay, and as Cole points out, we have now just learned how to integrate ln of x. It's right here. X ln of x minus x. That's the antiderivative of ln of x. How could you check? Take a derivative, you'll end up with a product rule. For some reason, there's this minus x floating around. The reason will become clear when you take the derivative. Magically, you'll get ln of x when you're done. All right, let's take a look at part C. E to the 2x sine of x. So I'm just putting it out there. You are not going to like this one. So don't throw tomatoes at the end when you figure out that you don't like this. I'm trying to lessen the blow here. You're not going to like this. You cannot throw shoes. I'd rather have tomatoes than shoes. Okay, so here we go. Let's set it up same way. Go ahead and put the 4 names. Don't even worry about what goes where yet, but there's a U and there's other stuff. So get in the habit of putting them in the same places. You don't need to put them in my places, but come up with some way that is reasonable to you. Okay. So when you take an antiderivative of e, does it get better, worse, or about the same? About the same. Okay, so that's a good candidate for being the thing in the right-hand column, because e doesn't really get any worse when you take antiderivatives. How about when you take antiderivatives of sine? Better, worse, or the same? About the same. So actually here we have freedom. We're free to choose which one we put in either spot, and they're both going to work. But I will say this. Would you rather take antiderivatives of e to the 2x or antiderivatives of sine of x? Yeah, I think a bunch of us see that 2 is going to involve a little u substitution. So just to avoid that, it would still be okay, but just to avoid it, we're going to put the e part over here and the sine over here. Fill in the bottom row. We need 1 derivative and 1 antiderivative. Make sure you don't forget that extra 2 in the du, and the negative sign for the v, and also dx goes every time. Okay, draw the arrows. And let's go ahead and write what we get according to the formula. So just write out that formula with these pieces. Don't forget the minus sign and the integral sign. Okay, so far so good. Yeah. So first I'm going to clean this up just a tiny bit. What can I take out of the integral? The 2 and also the negative. So let's take both of those guys out. So the 2 comes out front, negative comes out and turns it into a plus. Okay, and now we ask ourselves, are we in a better, worse, or the same position as we started looking at this new integral and comparing it to the original integral? Tiffany, are we okay at this stage? Okay. Better, worse, or the same? The new integral and the original. Seems about the same. We had e times sine, now we have e times cosine. What do you think we're going to do? We're going to do it again. So let's do it again. So over here, that's a good insight that you've got, Cole, because Cole sees that if we do it again, we're going to end up with essentially the same thing again, but something weird but good is going to happen. So just looking at this integral, I'll ignore the 2 and I'll ignore the stuff in the front. We're going to set our pieces up. Again, we have a choice to make, and you can make either choice. However, we need to make the same choice. Otherwise, we're going to get stuff that cancels, and we'll have something that says basically 5 equals 5, which is true but not helpful. So be consistent and make the same choice here. So what goes inside of the u? E to the 2x, and now the trig function is still over here for the dv, right? If you switch them, there's nothing wrong with that, but you're going to go backwards. So fill in the bottom row. Don't forget the 2 and the dx. Be careful with the plus signs and minus signs. Draw the arrows. And let's see if we can write everything out. So I'm gonna go back and write it like this. So I is the original integral. I'm gonna copy the first part, which I ignored before. Well, yeah, I mean, if they cancel, then that's bad news, right? Because we're trying to find what the integral is equal to. So we don't want them to completely disappear. But it feels like they might, right? So let's see what happens here. Plus 2, and then I'm going to put big brackets, because the red thing right there is a whole new integration by parts. So first, everybody see what we've copied? We'll highlight some stuff that's the same. All of that is the same as all of this. And the thing underlined in red, that integral, we're about to do a integration by parts on. And we're going to put the result down here in the brackets. First, everybody see all the pieces so far? Okay, so integration by parts, we're following our arrows. What goes first for this second integration by parts? So e to the 2x times sine of x. So we put that in the beginning. E to the 2x times sine of x minus integral. What goes next? Yeah, 2e to the 2x. I'll put the 2 in the front. 2e to the 2x sine x dx. Good. It doesn't look any better, right? And Cole was right. We have exactly the integral we started with. Started with e to the 2x sine x. There it is again. But let's persevere just a tiny bit longer. And I'm going to write it like this. Original integral equals, copying the green, distributing that 2. So what's the coefficient on the last term here? Is -4. What's another name for this integral? Can we call it I? Right, it's I. It's the original. That's what Cole said. So how are we going to solve this equation for I? We're going to add what to both sides? We're going to add that 4i to both sides. Okay. Ernie predicted maybe the i's would cancel, and if it had just been I and a single I, they would. But here they have different coefficients. And if we just add 4i to both sides, well, David says it's clever. That's much better than shoes or tomatoes. So add 4i to both sides. And we get something we can solve. 5i is equal to all of this stuff. So how do we solve for our original integral I? 5 by 5. And we'll have our answer. At some point, we need to put a stamp, so throw it there. Okay. Weird, neat, clever. What is this? Weird, all the above? I was my name, and I didn't make it clear. The very original integral, I just called it I. And now we see why I gave it a name so that we could solve for it. Yeah, that's the I. Yeah. Okay, so coming back to Garrett's question, how do we know? Well, I mean, I don't know. Apparently the other day I discovered I've been doing this for 18 years, and if I see E and sine or cosine, I know it's this weird thing. Do it twice and magic will happen. What we'll find, and maybe we're finding it already, is that there's this fundamental difference between the Calc 2 take a derivative, Calc 1 take a derivative, and Calc 2 take an antiderivative. Calc 1, just got to learn the rules and you're fine. Calc 2, there's a lot more experience involved. Right now we're learning some techniques. I can't call them rules because you can't just apply them willy-nilly and know that it will always work. We've got all these techniques. We're going to gain the experience that's going to decide which of these techniques has potential. Last semester, we didn't use the word potential. Just take a derivative. But here, taking antiderivatives, it's really about finding the possible potential ways to solve it. Okay, we have 7 minutes or so. That's like 30 seconds per. But let's see what we can do. There are some suggestions there. You can read through them and see how far you can get. There should be an answer key at the end.